Here we have a DC to DC converter, and we're going to run two popular and important tests. Test number one is, when does this turn on? So we're going to ramp up the voltage and see when we get a stable DC output. And second, we want to know, when the load current changes, how much does the output voltage droop? Basically, how stable is our DC to DC converter as our load changes? To run these tests, I'm joined by Alan Wadsworth. Alan, thanks for being here.
Thank you, Daniel.
So walk me through. We have a DC to DC converter.
Right.
How is this thing configured, and how are we actually going to run these tests?
So to do this testing, we have to have basically something on the output that can act as a load. Now, in the case of this product, you could use a source measure unit because that can sync and source. We also have electronic loads. So I'm going to set up the electronic load to sync 100 milliamps, and then I'm going to set the input to ramp from 0 to 12 volts. And I want to monitor the voltage on the output and the voltage on the input and see when does this guy actually turn on.
All right, let's set it up, take a look.
Okay. Starting off, I've got the load, electronic load, which is the output, and that's very simple. I'm just going to set it up to do a constant 100 milliamps current draw on the output. Now, in the case of the input, I'm using the feature of this box that allows me to create arbitrary waveforms. What I'm doing here is going to set up the input to do a voltage ramp from 0 to 12 volts. So I'm using the arbitrary waveform feature of this box. So on the input to the DC to DC converter, I'm setting it up as a ramp. And you can see here that I got this set up. It's basically, for 1 second, going to be at 0 volts. Then it's going to ramp within 2 seconds to 12 volts. And it's going to stay there for about another second.
And because we expect 3.3 volts out of this, ideally, as soon as the input voltage hits 3.3 volts, it'll turn on. But because there's some other circuitry that has to happen here, we want to know, how much do I actually have to provide this thing for it to stay on? Why does that threshold matter?
Yeah, well, it's important, obviously, to know, exactly when it turns on. But it's also important to understand that the DC to DC converter is stable over a wide variety of input voltages, right? Because you may not be getting 3.3 volts all the time. You may be getting different ones. And again, the spec is at least up to 12 volts in this guy. So I want to look at the entire range that it supports.
So it should work with a 4-volt input. It should work well with a 12-volt input.
Exactly.
And we just got to know that it's going to work across that whole range.
Exactly, yes.
Okay.
Now I've gone to scope mode. I've actually got this set up to do a single sweep, and I'm going to trigger off when I actually hit the arbitrary run button. So as soon as I hit the ARB button, it's going to start taking data, and then it's going to do one single sweep and stop.
Okay, so let's turn on the ARB and see what happens. So the ARB's running, it's capturing. We know it's a couple seconds long, so it'll take a moment, and we're going to see it probably all at once. We expect a ramp and then like a square wave of the thing turning on. So there it is. We have our ramp. We see it turn on. How do we figure out which voltage it turned on at?
So if I press the scope button once, the markers will appear. Right now I'm looking at the input waveform. Now move the marker over to where it looks like it's about to turn on or turning on, and you can read at the bottom that it's around 3.6, 3.7 volts, which makes sense because, again, there has to be a little bit higher than 3.3 volts to actually turn on. And then, of course, I can move the marker over here and see as it obviously goes above that voltage, it's pretty stable. It's 3.3 volts.
So we have a very stable output across a wide range of voltage inputs like we expect.
Correct.
The other test we want to run is, currently we're only, no pun intended, drawing 100 milliamps. But now we want to say, what if that current is changing?
Exactly.
What happens to that square wave, our output voltage? How much does it wiggle? So are we going to do another ARB with the current? Can you walk me through that setup?
Yes, I can. The next setup, we're going to basically have the input voltage stable. I'm going to put it at 8 volts. And then I'm going to apply a current pulse. So I'm going to start off at 100 milliamps, change it to 600 milliamps for a couple seconds, and then go back down to 100 milliamps. So again, I want to look at the output voltage as I'm doing that.
All right, let's set her up.
So in this case, you can see that I've specified on the output, I want a current pulse. So you can see it's in current priority mode. And I've got it set up as a pulse, obviously. And in this case, again, I've set up the pulse to start at 100 milliamps for 1 second. Then for 2 seconds, it's going to go to 600 milliamps, and then back down to 100 milliamps, and then go back to 0.
And we know we expect the output voltage to drop when the current ramps.
Correct, yes.
The question is how much. And in some situations, it might be too much. If I'm really relying on that for a tight timing performance, and it's drooping when something else happens, that could cause big issues with my
Exactly, yeah. And again, sometimes you want to check just to see if your DC to load is working correctly or if it's gone bad or something like that. So there's lots of reasons you might want to check out the DC to DC load performance, yes.
All right, so let's see how this one does.
Yeah. Okay, so now I've started the scope view, push the ARB run button, and it's going to take, again, a few seconds to go ahead and make the measurement, obviously.
And here we have a waveform. We have the steps we expect. Again, the question is, how much did it change?
So again, you can see on the bottom, I can see my current pulse, and on the top is the voltage. So I can change the vertical scale on the top here if I want to. Move this down a little bit. But yeah, you can clearly see the voltage is changing. If I push this scope button again, I get the markers back. And let me move this marker out of the way. So you can see here, as I increase the load, yes, it does droop a little bit. It's like 3.29 volts. Over here, it's 3.31. Yeah, so there's a slight voltage drop as I draw more current. And again, as I go, I can follow this along. And I see as the current decreases, I'm back to my 3.31. And you can even see a little bit of a change here as the whole thing turns off entirely. But yeah, very easy to look at the voltage change versus current using the markers on the front panel.
So really, we didn't see much change at all. Only 20 millivolts between it drawing 100 milliamps and it drawing 600 milliamps.
Exactly, right.
So that's pretty stable, pretty good. I'd feel good about the inductor choice and everything on there.
Yeah, of course. And that's what you want to see. I mean, if I'd seen a big difference, then I'd start to question something's wrong, it's defective, or I picked the wrong DC to DC converter. But yeah, it should be very stable. But again, you can see this very easily with the equipment.
So we talked through two essential DC to DC converter tests. We checked the turn-on threshold voltage, and we checked the load regulation.
Right.
Awesome. Well, thank you, Alan. This was great.
All right. Thank you, Daniel.
Learn more at keysight.com/find/DC power analyzer.